Okay. Hello to everybody. Good morning. So it's a pleasure to introduce to Virginia Cuomo. Virginia Cuomo was my PhD student together with Enrico Maria Corsini. She defended the PhD at the University of Padova just now three years ago, and she is now in Universidad de Atacama for her first postdoc. So Virginia is an expert in dynamics of bar galaxies and properties of bar galaxies. And especially Virginia is an expert in measuring pattern speed in bar galaxies with one method which is called the Tremaine-Weinberg method. And this is the subject of the talk today, basically, open question on the bar pattern speed with the Tremaine-Weinberg method. Virginia is visiting me until December 16 this year, so she is going to be here for 2 weeks more. And she is a very good collaborator of me working on this subject about bar galaxies. So Virginia, it's a pleasure that you are here, and please go ahead.
Thank you. Can you hear me well? It is fine? Okay. So I'm very happy to be here. I had the chance to spend here at the Institute some months during my PhD, collaborating with Alfonso. So it is always a pleasure to be able to come back here and visit Alfonso and the Institute. So today I will speak about this topic, which I have been working since my PhD, and some results obtained during the last couple of years. I am from University of Atacama, which is a small university located in a small town in the north of Chile, in the desert, more or less in between Paranal and La Silla Observatory. So working there with Lorenzo Moretti. So let's start. Some very few details about barred galaxies and why we want to study bars. Because they are very common structures. They are located in a large fraction of nearby galaxies, and since the first morphological classification, they have a very important role. They can contribute to a large fraction of the total galaxy light, and they have a complex role in the evolution of their host. So, for example, they during their evolution, they exchange angular momentum, and this can lead to the redistribution of gas in the central part of the galaxies, where they can favor the formation of inner structures, such as disks and nuclear rings. They can also regulate the star formation rate, and in particular, they can lead to the formation of a region where the star formation is quenched, called the dark gap, just outside the bar. So in order to understand better how bars influence the evolution of their host, we need to measure some properties of these structures. So the properties of the bars are mainly three. The bar radius, which is basically the extension of the stellar orbit which supports the bar. And we have different methods based on the analysis of galaxy images to derive this property. We can use, for example, a photometric decomposition where we include a parametric law to describe the bar, or we can analyze the radial profile of the position angle, ellipticity of the isotopes described in the bar, or we can use a Fourier analysis. Since the bar is associated to other components, such as rings or spirals, it is not always very easy to identify the age of the bar. The second parameter is the bar strength, which is a quantification of the contribution given to the galaxy potential from the bar. And it is always used to distinguish between weakly and strongly barred galaxies. But maybe the most important and most interesting property of the bar is the bar path speed, which is basically the angular frequency of the rigid rotation of the structure around the galaxy center. To compare results coming from theoretical studies and simulations with observational studies, the bar path speed is usually parameterized by the bar rotation rate, which is defined as the ratio between the co-rotation radius and the bar radius. The co-rotation radius can be derived as the ratio between the circular velocity of the galaxy and the bar path speed. So here we can see the relation between the bar rotation rate and the bar path speed. And it allows, this bar rotation rate allows to distinguish between fast and slow rotating bars. If the rotation rate lies between 1 and 1.4, the bar is defined as fast rotating, while if the rotation rate is larger than 1.4, the bar is defined as slow rotating. We cannot observe a rotation rate slower than 1 because this corresponds to an instability of the orbit of the star supporting the bar, so the bar dissolves, but we can refer to this case to ultra-fast bar. The value of the bar rotation rate does not depend on the absolute value of the bar path speed. Indeed, in the sense that if we look at the radial behavior of the angular frequency of the galaxy and we choose a given bar radius, if the bar extends more or less up to the rotation radius, we will have a ratio between these two radii which lie in the fast regime. So the bar is defined as long or fast, and we will have a given value for the bar path speed. While if the bar extends, it is shorter with respect to the rotation radius, we will have a different bar path speed, but we will have that the ratio of these two radii will be in the slow regime. And in this case, the bar it is shorter with respect to the rotation. So there are several methods that has been used and proposed in literature to derive the bar path speed and consequently the bar rotation rate. Here there are some examples. So for example, we can use the location of dark gaps or of the dust lanes or of the rings to identify the rotation of the resonances and the rotation radius in a galaxy, or we can model the morphology of the gaseous kinematics with some simulations to derive the rotation. All these methods are related to submodeling, but there is only one way to directly derive from some observable quantities the bar path speed, which is the Tremaine-Weinberg method. And we are going to see some details about this later. So why are so important the properties of the bar in the context on the evolution of bar galaxies? First of all, because of the formation mechanisms. There are, let's say, three mechanisms leading to bar formation. Here we are going to see the two main mechanisms. The first is internal instability, which is expected to lead to the formation of fast rotating bars. And then we have interaction, which are expected to lead to the formation of slowly rotating bars. Then during the evolution of a bar galaxy, bar is exchanging angular momentum with the other structure of the galaxy. And this leads to an increase in bar radius and bar strength, while the bar path speed is decreasing, and the bar rotation rate is pushed in the slow regime. Related to this, if there is a huge amount of dark matter content in the central part of the galaxy, this dense halo should exert dynamical friction on the bar and as well produce a slowdown of the rotation of the bar. So studying the bar properties, and in particular the bar rotation rate, can give us some information about environmental effects and evolution of bar galaxies. So some few details about the Tremaine-Weinberg method to get the bar path speed. So it has been proposed by Tremaine-Weinberg in the 80s, and to apply it, we need both photometry and spectroscopy. Here you can see a Muse reconstructed image of a bar galaxies over which are overplotted some pseudo-slits, which are aligned with the disk major axis and crossing the bar. So we need to use dedicated long slit observations. This was the first application of the method were exactly performed using long slit spectroscopy. But nowadays, with the integral field spectroscopy surveys, we can use public available data and define a posteriori this pseudo-slit. We will need to use a tracer that satisfies the continuity equation. So usually we use the stars in the galaxy, even if there are some efforts to use the gas, but still on debate. And we are going to measure these two quantities, the photometric and kinematic integrals, which are the luminosity weighted average position and line of sight velocity of the stars along each pseudo-slit. Here you can see the luminosity weighted average position and line of sight velocities measured along the central and the offsetted slits. The central one is the red one and the green are the offsetted. And you can see that the position of the stars, the line of sight velocity of the stars are centered in the center for the central slits, while the peak is a little bit offsetted when going to the offset slits. And this offset is what we are measuring as integrals. So if we plot the kinematic and photometric integrals for each slits, they are going to be aligned on a line, and the slope of this line is giving us directly the bar path speed. So there is quite a simple, let's say, equation, but this implies strong request, in particular in identifying the right target galaxies to be analyzed with this method. So for example, we need to identify galaxies with an intermediate inclination. We need to find bars that are not aligned with the main, with the major or minor axis of the disk, because otherwise we are not going to be able to cut the bar with any slits or to measure some signal in the integrals. We need to have a well-determined disk position angle in order to properly locate the slits. So we need to perform a preliminary analysis, maybe from photometry or from kinematic, to derive the disk position angle. And so we cannot use galaxies that are that host disturbed disk, maybe that are interacting or that are hosting asymmetric structure in the disk. And then we need to have data that cover the asymmetric portion of the disk, because the disk must give an asymmetric contribution along each slit. So what are the results coming from the Tremaine-Weinberg method obtained in the last years, especially with the advent of integral field spectroscopy? Here we can see some results from Guo et al. In 2019, where they applied the method to 50 galaxies from MaNGA. And here we can see that the barotracer rate with respect to the dark matter fraction within the effective radius of the galaxy does not present any clear trend. Even if we can see that there are some interesting things. For example, these red points are bars that are located in the ultrafast regime. And then also the other point is that there are some bars in the slow regime, but the error associated to this bar rotation rate measurement are very high. So it is very difficult to give a strong conclusion about that. Here we can see some results from our paper in 2020, when we collected all the galaxies analyzed so far in literature based on the Tremaine-Weinberg method, and we explore correlation among bar properties and properties of the galaxies. And we confirm preview results, and we observe in particular that stronger bars are also longer and are also rotating with a lower bar path speed. And this is in agreement with the fact that probably, and are also in more massive galaxies, in agreement with the fact that probably more massive galaxies had more time to form a bar and to let it evolve towards a long, strong, and slowly rotating bar. More recently, in 2022, Garmo-Emichen analyzed a sample of 25 Milky Way analogs from MaNGA, and they compared the results with the one from for the Milky Way coming from literature. Here we can see the distribution of the bar path speed in their sample compared to results coming obtained for the Milky Way. The Milky Way bar path speed can be found with different methodologies, including one adapted Tremaine-Weinberg method. And they claim that their results are in agreement with what is found in the Milky Way. I would say a little bit smaller in the bar path speed. But from all these results, we can see that there are some open questions in the related to this topic. Here you can see, in these figures, you can see the bar radius versus the co-rotation radius. So this plot is showing us the bar path speed, the bar rotation rate. Indeed, in this triangular region are located the fast bars. This region is associated to the ultra-fast regime, and in these regions should be located the slow bars. So if you exclude results with very large errors, which are the gray points, we do see that most of the galaxies are basically compatible with the fast regime, while there are a lot of bars that are the blue points that are in the ultra-fast regime. So there are no genuine slow bars, except for one that has been recently presented in this paper, and there are a lot of ultra-fast bars. So the first topic question is, what are these ultra-fast bars? Are they a mistake or an issue related to the application of the Tremaine-Weinberg method, or are they coming from an incomplete understanding of their nature? They are, indeed, they are theoretically unexpected, but they are observed in almost 20% of the Tremaine-Weinberg-based measurements. They are found in late-type galaxies, mainly, and this is confirmed also in this recent paper, where they were observing basically late-type spirals, and they found a larger fraction of ultra-fast bars. Here you can see the green point, again, bar radius versus co-rotation radius. But they also have been observed using other methods rather than the Tremaine-Weinberg method. So we need to understand better what they are. The other open question is related to the lack of slowly rotating bars. So in the framework of the standard CDM cosmology, all simulations show us that the rotation rate should be in the fast regime, especially for a high value of the dark matter halo angular momentum, which can be gained from the bar. So these expectations were not confirmed by observational results coming from the Tremaine-Weinberg method. Moreover, we need to remember that bars triggered by interaction are also expected to be born. And since the interaction should be an efficient way to form bars, it is, again, it is strange not to find so many slow bars. Recently, cosmological hydrodynamical simulations, Illustris and Eagle, again revealed this tension between simulations, expectation, and results. Here you can see again bar radius versus co-rotation radius, the color points. I don't know what I did. Okay. The color points are coming from the simulations, while the gray points are the results coming from the observation studies. And you can see that also in Illustris and Eagle, bars should be slow, actually are slow. Even, yes. Okay. Yeah, okay, I will be happy. Okay, so there is this discrepancy even when the measurement from simulations and observation are performed exactly in the same way. Also, there are other possible explanations for this discrepancy. So, for example, there is this paper, recent paper by Fakudi in 2021 that alleviates tension. So, of course, there are possible other explanations. So the question is dynamical friction actually acting on galaxy bar, or maybe are we not from the observational point of view targeting the right target of galaxies possibly hosting slow bars? So to try to answer to the first question, we select all the ultra-fast bars included in Khalifa. So we have 12 ultrafast bars from Khalifa, and we explored the two ingredients needed to define the Barrow-Tesseract. First of all, we confirmed that the morphology of these objects, basically they are all Lie-type galaxies, and they can host often rings or strong spiral arms, which may affect the application of the Tremaine-Weinberg method. We revised the application of the Tremaine-Weinberg method for these galaxies, and in particular, we checked the geometrical property characteristics of this galaxy, inclination and orientation of the bar with respect to the disk axis, to see if there are some clustering. You can see the green points are the ultrafast, some clustering with respect to the error associated to the various bar quantities, the right bar quantities, and we did not find any bias. We tested that the Tremaine-Weinberg method is correctly applied, so we decided to focus on the other ingredient needed to define the Barrow-Tesseract. So in general, to derive the bar radius, to do this kind of analysis, in literature, people use different methodologies and derive a mean bar radius coming from different methodologies. This is because various photometric methods used to derive the bar radius have different limitations, which are due to the limitation of the method itself, but also the limitation that can be associated to the specific object that we are observing. So usually we use a mean value. So in this case, what we did, we use a different approach to derive, to test our mean. And in particular, we use the map tracing the transverse to radial force ratio, which is, we started from the image of the galaxy, we derive the gravitational potential from Poisson equation, and we plot the transverse to mean radial force. We derive the transverse and radial forces acting on the galaxy, and we plot this map in polar coordinates. In a barred galaxy, this kind of map should be characterized by 4 thick slabs, plus a peak or a plateau in the radial profile of the mean to radial force ratio. So this method is generally used to identify barred galaxies from these two characteristics. Also, this method can be used to provide a new bar length estimate, which corresponds to the red, to the peak in the radial profile, to the red vertical line, which corresponds to the peak along these 4 slabs. And if we plot this line in angular, in the angular profile, we will have 4 peaks, which correspond to the 4 corners of the bar. So with this method, we have a new estimate of bar radius, but most important, we can test the reliability of our R mean, because we can see the blue line correspond to R mean. We can see where in this ratio map is going our R mean from literature. And we do see that in most of the cases, the bar radius used in literature is not in the bar region, but outside the bar region. So we do not observe the typical 4 peaks expected for a bar galaxy. So in general, the new bar length coming from this method, it is almost 50% shorter than the mean radius used in literature, that it is usually outside the bar region. So if we use the new bar length, we do see that the ultra-fast bar actually are going back to the safe fast bar region. So the other open question, the lack of slow bars. In order to try to answer to this question, we try to push the question of slow bars to a promising sample of galaxies which should host slowly rotating bars. And so we focus on dwarf bar galaxies. These objects are common in dense environment clustering groups where they can suffer also because of their low masses. They are prone to suffer for interactions, which should form bars, slowly rotating bars. But they also expected to host massive and centrally concentrated dark matter halo, which should slow down the bar through dynamical friction. Unfortunately, these objects are of course small and faint, so they are very difficult to be observed and to perform this kind of analysis. There is only one Tremaine-Weinberg application of this kind of object, performed by Cosine et al. 2007, which revealed a fast rotating bar with a large area. So we decided to focus on this class of objects, which are nowadays known to host a lot of characteristics, different ranges in rotation, but also different hidden disk structures, including bars and lengths. So we wrote a dedicated ISO proposal for news data, and we got time for these 6 objects that are dwarf galaxies located in the Virgo cluster. We ended up with 5 candidates that are the red points that are located everywhere in the cluster. They have stellar masses, let's say between 10 to the 9 and 10 to the 10, so they are not very dwarf galaxy, they are low masses galaxies, and they are member of the Virgo cluster, so they must be prone to have suffered from some environmental effects. Okay. So first, I will present you the results from a peculiar case, which is the first one of the galaxy in our sample, which is EC3167. Here you can see the Sloan image, and overplotted the squared are the muse pointing that we got. So this object has been recently accreted into the cluster together with a group of galaxies, and it reveals a bar with a peculiar triangular shape, which we interpret to be as a loop-sided bar. So loop-sided bars are asymmetric bars which are located in off-centered disk, but which also have an asymmetric shape. So the best object, the best example could be the Large Magellanic Cloud. Here we can see some loop-sided bars observed from illustrious simulations, which reveal that this shape, this object could be long-lived property of bars, which can be born like this, loop-sided, or become so during the evolution, and can be formed through interaction, or can be formed in an off-centered disk. We performed an isophoton analysis of this galaxy. Here you can see the radial profile of the server dryness, position angle, and ellipticity, and P3, which measure the deviation from the symmetry of the ellipses that reproduce the isophoto of the galaxy. And we do see that there are some asymmetries in the bar region. And we also produce a Fourier analysis in which we do see a peaked n equal 2 component, typical for a bar galaxies, but also strong or non-negligible n equal 3 and n equal 5 odd components, which are associated to the asymmetric nature of this. Using the Muse data, we derive the stellar kinematic, and from this we model the circular velocity from a kinetic correction, and we apply the Tremaine-Weinberg. And we derive that this bar is rotating slowly, suggesting that probably if the formation of these bars is produced by an interaction. So to conclude, some results coming from the entire sample. Here you can see the remaining 4 objects. Here we are using deep imaging from the next generation microsurvey, and overplotted are the muse pointings. We are performing a careful photometric analysis to identify the bar, and then to derive the bar length using different methods. We measure the stellar kinematic for the object, velocity, error, stellar kinematic error, and then we derive the circular velocity from the rotation here I show you the rotation along the major axis, and you will see that the values are compatible with low masses galaxies. And then we apply the Tremaine-Weinberg method to the new data cubes using two different spectral ranges corresponding to the two different colors of points. And here are the rotation rate resulting from this analysis. We have a galaxy with no Tremaine-Weinberg signal. This is because probably the bar is oriented parallel to the disk minor axis. And then we have two genuine slowly rotating bars and one fast bar. So if we plot, the black stars are our dwarf galaxies. If we plot our results in the correlation obtained for all the galaxies analyzed before, we do see that bars in dwarf spark galaxies are short, quite weak, and they have low value for the bar with respect to their massive values. Here I plot the bar rotation rate for our dwarf galaxies corresponding to the squared versus the absolute magnitude of the galaxies with respect to results coming from literature. And we can see that there might be some correlation between these two quantities, which can be discussed in terms of the role of dark matter content, especially in low mass galaxies, or in terms of the formation mechanism in these low mass galaxies more prone to interaction. So it would be interesting to add some few points here to see what is going on. So yes, so the summary. So we have seen the properties of the bars that are needed to characterize the bars and to interpret and to understand something more about the formation of bars and the evolution of bar galaxies. We have seen the Tremaine-Weinberg method, which is one of the methods that can be used to derive this quantity, and which are the open questions related to measurements coming from the in particular, ultra-fast bars that are not directly affected can be explained by a wrong measurement of the bar radius, while slow bars could be expected in dwarf bar galaxies, even if we might need to explore a little bit more this part of the mass bar rotation rate. So these are the references, and thank you for the attention.
Okay, Virginia, thank you very much for your nice talk. Let's start. John.
Thanks. Well, yes, very nice talk, nice work. And first of all, let me say that the Tremaine-Weinberg method is good. No question about it. You mentioned Font et al. Method,
yes.
And we've published now 7 papers using Font et al. Method. And we've shown in one of them that it is completely equivalent to TW, to Tremaine-Weinberg, but that it gives more results.
Yeah.
So that's one thing, but that's not very important. The important thing to say in all of this work is that the criterion of 1.4 between fast and slow is meaningless. It's not meaningful, it's wrong. And the reason it's wrong is very simple, because it doesn't take into account the evolutionary growth of the bars. The bars grow with evolution. So you take a pattern speed which is moving outwards as the bar slows down and makes the ratio R get bigger, go to 1.4, 1.5, and so on. But the bar is growing, so the ratio gets smaller. So we used simulations by Inma Martinez Alcuesta to show this. This is very clear. So in any particular galaxy, you may have slowing down by the halo, therefore migration outwards of the co-rotation radius, you may or may not have also bar growth, which changes the value of the ratio. So a galaxy you may think is fast, may be slow. A galaxy you may think is slow, may be fast. And so the use of these criteria is not based on physics. It's arbitrary. The initial simulations by de Battista and Selwood were missing things. They were not complete. So most of the work in this field is based on that wrong premise. That's what I really want to say.
Well, I think that, yes, I think we try to explore a little bit also the role of the bulge to see if there are any correlation between the bulge and the various parts of the field.
Yeah.
But with the sample of galaxy, sample of 100 galaxies that we had not enough bulge properties measurements to infer any. But
your observational work, your conclusions of the range of these are very good, and not to be criticized, they are really good. But for example, in our methods, we can measure the co-rotation of nuclear bars as well. We can go much smaller. We've measured the co-rotation rates of nuclear bars, and we've measured that ratio, the ratio of bar length to co-rotation radius, and it's different for the nuclear bars than for the bigger bars. Well, there's a lot more things you have to do. I'm saying the work you've done is fine, is very good. And all of the work that Jose Alfonso has been doing over the years, sorry about that, is very good. But there's a fundamental misconception about the whole thing, and I think you should know about that.
If I can say something, it's true, John, that the 1.4 and 1.7 about the slow and fast bar is just a consensus. It's not a physical. It's not indicating a physical indication. But what is clear in the plot that Virginia showed, that when you compare simulation with observation in this diagram, radius of the co-rotation versus radius of the bar, there is something missing here. We are measuring during the last 20 years pattern speeds with the Tremaine-Weinberg method. These are the gray points, and the gray points are much below the simulation says. And there is something there. There is something there in the simulations, of course, because the observations are the observations. But there is something on the simulations that the simulations produce a slow bar, or whatever you want to call, that they are not observed in nature. In the simulation, there is something. Okay, so this is true. We can discuss.
When you're here, we could talk. I think the problem is with the simulation, really. I think that's the problem.
Yeah, I think so.
Yeah, so really nice talk. I have two questions. I will maybe start with the easiest one. So with your dwarf galaxy sample, at the end, it seems that you get basically two branches with the evolution of the luminosity and the surface brightness. Yeah. So do you have enough measurements with your observation to also measure the dark matter profile of these galaxies to see if a core cusp galaxies get these two different branches? And so the question is, in 2 years ago, there was some simulation made by the team of Ivan Mitchev on ILMI that was showing that with the Tremaine-Weinberg method, in some circular galaxy evolution, you can see some strong variation of the velocities with time, with the amplitude of the velocities, which is anti-correlated with the length of the bar in order of 20% in really short time scale between 50 and 200 million years old. And of what I understood, basically in your observation, you also try to impose that the bar is not aligned with the arm, right? Or at least with the length of the arm. So I'm not biasing sample with this because basically it's where it's at that moment that they detected that the bar is going faster. And the problem is that the variation of the velocity of the bar is due to the reconnections with the spiral arms of the galaxies, which means that with the Tremaine-Weinberg method, you're going to detect something which is longer, also to decrease the velocities at a given time. So. Yeah, because basically what they show is that it's when you are off of the major axis of the galaxy, basically it's where the bar is going the faster. So maybe you're biasing this to get to find the fastest predicted bar there. I'm saying that because in the Milky Way we have a discrepancy of the measurements that we have, where you have dynamical measurements that show that it's around 50, and Tremaine-Weinberg method show it's mostly a slow bar of 39, 40 kilometers per second.
Any other question, comments? Good. So thank you very much again. Well, in the audience, we have some comments or questions.
If someone in the audience on Zoom want to speak, unmute yourself and ask a question. Okay, so if not, let's thanks again, Virginia. And there is a scientific coffee in the cafeteria.